Hello everyone, and welcome to my channel. This channel is an educationally directed channel, and we try to tune you into some great theories of everything, all-encompassing theories, and just really anything that I think could benefit your life, but that you probably don't know about because it's knowledge that has been suppressed and knowledge that requires a great deal of digging to suss out. Today is our 442nd video on the reciprocal system of theory from Dewey B. Larson. Mr. Larson proposed his two fundamental postulates in 1959 or so, and they were just two sentences about how the universe operated. And then he took those two fundamental postulates and he, through a process of deduction, he arrived at a theoretical universe, kind of an if this then that approach. I believe about 165 steps that I outlined in some videos I did probably a year plus ago that you could find. They're called the outline of the deductive development of the reciprocal system. And about 165 steps to define a theoretical universe. And then he took his theoretical universe and compared it with the measured empirical universe of the scientists, the chemists, the astronomers, and then wrote up the comparison in his books. We're looking at his book on one of his books on chemistry called Basic Properties of Matter, where he arrives at through deduction from the postulates at equations for some of the various properties of matter, such as the melting point and the compressibility and the interatomic distance, and then compares them with the scientific tables. It's an interesting study, and we are on chapter 5 here that is on heat. And he goes through kind of the process of how he formulates his equations, and then talks about some of the finer points. It's fairly in the weeds. There's a lot of detail involved. We're wanting to give Larson his voice. Because he deserves to be heard, but also because I'm not really a competent translator of the whole thing. You know, I'm trying to learn this myself. If nobody else is going to do it, then I'm going to do it. But I'm not really terribly competent to do this. I don't know that anybody is, but so I'm just trying my best. But you know, if I try to put it in my words, I don't always get the words right. So I'm just going to read from him most of the time. Now, you may be asking, what are the two fundamental postulates? Well, the first postulate and the most important are one that is really the only important one. The other one is just having to do with math and geometry. And it also has been disputed by some of Larson's followers. But the first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, and then the second postulate is the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Basically, kind of just saying 2 + 2 = 4, and 4 means 4, and these XYZ coordinates, and we're dealing with, the basic things that you kind of have to accept in order to be a scientist or a mathematician. But the first postulate, he's saying that the universe is made out of motion. Motion is the relationship between space and time. In particular, we're talking about a specific kind of motion that he calls a scalar motion. This is a motion that has a magnitude but has no specific direction. This motion can be visualized using a balloon that you put dots on. When you blow up the balloon, all the dots will be moving away from each other, but not in any specific direction, or really in all directions. Every dot will be moving away from every other dot. And same is true when you suck in the balloon. Every dot will be moving toward every other dot, but in no specific direction. Larson refers to these as the outward motion as the progression. The inward motion is gravitation. And this is, so motion in Larson's system, this scalar motion, is the relationship between space and time. Motion is basically a fraction with space or time as the numerator, time or space as the denominator. The most basic example is speed. Speed is a scalar motion. The car is going 15 miles per hour. 15 miles of space in 1 hour of time, space over time. If you decide to double the speed, then you can say the car is now moving 30 miles per hour. Or, alternatively, you can say the car is now moving 15 miles per half hour. You can either multiply the space or divide the time. That is a reciprocal relationship between space and time in speed. Larson generalizes that to apply it to all of our other scientific phenomena, such as matter, energy, force, acceleration, momentum, pressure, temperature, power, electrical charge, magnetic flux, permeability, permittivity, surface tension, viscosity. These are all forms of motion, and they all have their unique space-time configurations. Keeping in mind that part of that postulate is that space, time, and motion all come in 3 dimensions. You can see the 3 dimensions of space kind of right in front of our face. X, Y, Z coordinates in a still frame. That's kind of the way that we experience space. You can quibble about the number of dimensions, but Larson says 3. And then we are moving through time. So we see 3 dimensions of space in a still frame and time moving in a scalar manner. Time is always getting later and later and later, but in no specific direction. This is kind of like the process of abstraction. If you've got that expanding balloon, or say you've got the contracting balloon, all the dots are moving toward each other, but in no specific direction, until you abstract and you arbitrarily stop the motion of one of the dots, and you say, for the purposes of my, of this, I am arbitrarily deciding that one of the dots is motionless. And then when you do that, then you can start measuring the directions and the vectorial directions, and you can start to, I guess, just make measurements and find directions. And it even looks like there are force fields then, because it looks like that stationary dot that you have, all of the other dots are moving toward it. So it looks like there's a force field emanating from your dot, and that there's a force of attraction that is, moving all the other dots toward it. But that's not the case. That's only the result of you abstracting and assigning a reference system. So that is really this coordinate space and clock time. 3 dimensions of space in a still frame and progressing time is the result of abstracting that original scalar motion and anchoring a spatial reference system. So you're anchoring yourself to space and thereby stopping space. And then you can start defining vectorial motions and so on. Okay, now let's plug in the discrete unit postulate. Universe is composed of motion existing in 3 dimensions in discrete units. Space, time, and motion come only in discrete units. So you have to have a full unit of space, for example, before you have space. If you don't have a full unit, then you don't have space. And same with time. And if you have 1 unit of space in 1 unit of time, you have 1 unit of speed. Space over time being speed. And this unit of speed, Larson refers to as unit speed, and it is also known as the speed of light. This is the empty universe of Larson's universe of motion. The first thing that you have to get with the universe of motion is the concept of motion without anything moving. Motion precedes the thing that's moving. So in a universe of motion, if you have nothing, you still have this outward movement of the progression in all directions at unit speed, or the speed of light. That is the empty universe. That is the what Larson calls the progression of the natural reference system. Okay, so that is Larson's natural reference system. We looked earlier there at the spatial reference system, coordinate space and clock time. And then if you have this natural reference system, that basically means that it is the center. Larson calls it the null point or the neutral point. You call the 0 point the origin, the ether. And half the universe is moving faster than that. Half of it is moving slower. Or I would say beyond, half is beyond and half is within. And the half that we're familiar with, he calls the material sector, the slower than light sector. And then this half that's beyond the speed of light is called the cosmic sector. And the cosmic sector is basically the reciprocal of the material sector. So in the cosmic sector, you have coordinate time and clock space. So you have 3 dimensions of time in a still frame, and you have clock space. Space is always getting farther and farther and farther apart, but in no specific direction. So this is basically the temporal reference system. So you have a reference system in space, a reference system in time, and then what he calls the natural reference system, or really the reference system of motion. And then within the cosmic, and so when you cross that unit speed boundary, you move from one sector to the other. But because of the discrete unit postulate, there are many regions within each of those 2 sectors. So within the material sector, where you have things like atoms and particles that interact in less than 1 unit of space, which is about 1/500,000th of an inch, microscopic to be sure, but very large compared to the size of an atom, you don't have space. And so the interaction occurs in time, because the universe is made out of space and time, motion, and if it's not space, then it has to be time. And so Larson calls that the time region. And when you cross the boundary into the time region, you also have to invert the rules again. And the progression is now moving inward, and gravitation is moving outward. And the same is true over in the cosmic sector, except with time. You have interactions of cosmic atoms and cosmic particles and cosmic molecules in less than 1 unit of time. Then you don't have time and you only have space. Larson calls that the space region. And the rules reverse. Now the progression is going in and gravitation is going out. This dynamic provides what he calls an interatomic equilibrium at the place where the progression, which is moving things inward, and gravitation, which is moving things outward, at that place where they're equal, there's an equilibrium established, and that is this interatomic equilibrium in the solid state. Basically the bonding. And then when you add pressure or temperature, pressure will shrink that, and temperature will expand that. And so we looked in chapter 4 on compressibility, the rate of compression. And now here we're talking about heat. And he's really saying that coming up with equations for heat, the main one so far, PV equals RT, or PV equals T, pressure times volume equals temperature, which he derived, and energy equals temperature, and energy equals is proportional to the 4th power of the temperature. But that within the time region, we don't see time, we only see space. We're anchored to a spatial reference system. And so whatever goes on in the time region, we can't see it because we don't see time. We instead see its equivalent in space. So we see the inverse of what's going on in time, that we see the inverse in space, but we see it as a 2nd power entity. So this E equals T to the 4th power has to be reduced to E equals T to the 2nd power. I still am not sure where he gets the idea that that radiation is 4-dimensional. He says radiation originates 3-dimensionally in the time region, and it makes contact 1-dimensionally in the outside region. Therefore, it is 4-dimensional. I don't get that at all, and I never have. But I'm not sure it's right, but I'm going to give him the benefit of the doubt, which is what you have to do when you are talking about paradigm shifting. You have to suspend disbelief and then evaluate it as soon as when you've had the whole picture, when you get to see the whole picture. Okay, so we'll start from there. I'll try to explain anything else that comes up here, like as far as atoms and molecules. Atoms are 3-dimensional rotations of that original outward progression with the interface of 2 photons, which are reversals of that progression as well, that turn into wave-like simple harmonic motions. Okay, we're going to start from here and see where we go. A modification of this relation, that E equals kT squared, energy equals a constant times temperature squared. A modification of this relation results from the distribution of the thermal motion over 3 dimensions of time, while the effective component in thermal interchange is only 1-dimensional. Okay, so this is related to being in the time region. This is immaterial as long as the thermal motion is confined to a single rotational unit. A rotational unit would be one of the rotations of the atom that is gravitational, so it's going outward. Okay, as long as the thermal motion is confined to a single rotational unit, but the effective component of the thermal motion of magnetic rotational displacement, or 2-dimensional displacement. An atom is a 3-number combination, 2 2-dimensional or magnetic rotations, and then one electric or one-dimensional rotation in the opposite direction. The two magnetic motions alternate, and the electric rotation is optional. It can be zero in the noble gases, and in other elements it can be positive or negative. Okay, so and that's what's so hard about Larson, is that he's always throwing in these terms that you have to know, and if you don't know them, then you need to look them up, and by the time you've looked them up, you spent an hour on one paragraph. So I'm trying to unpack this, make it as easy as possible for you, but it's not going to be easy, obviously. The effective component of the thermal motion of magnetic rotational displacement, N, is only 1 over n to the third power of the total, because there are 3 dimensions, I believe. We may therefore generalize that E equals kT squared equation by applying this factor, substituting the usual term heat. See, that's what I hate about when he does this, and other scientific writers do this too, is that they consolidate multiple steps in one equation. So like, it would just be fine if what he did was like he put in this third 3-dimensional factor, and then he said, okay, we had E equals kT squared, now we're going to have E equals kT squared over n to the third power. But now, instead of doing that, he says, we may therefore generalize this equation by applying this factor, substituting the usual term heat for the time region thermal energy. We have H equals T to the second power n to the third power. So he puts in this other thing that complicates it. But what he's basically doing is he substituted the symbol H for the symbol E. He puts in heat for the time region thermal energy. So he substitutes heat for the time region thermal energy. The general treatment of heat in conventional physical theory is empirically based and is not significantly affected by the new theoretical development. It will not be necessary, therefore, to give this subject matter any attention in this present work, where we are following a policy of not duplicating information that is available elsewhere, except to the extent that reference to such information is required in order to avoid gaps in the theoretical development. Right here, I would appreciate if he would have, and again, I'm quibbling with Larson, and he did a monumental job, but this is what I would personally, if he's telling me that he's not going to repeat the material that can be gotten elsewhere, at least give me a source so I can look for the material, because I'm not a scientist. I don't know where to go find information on the conventional physical theory of heat. Give me a source so I can do the research myself, instead of just saying we're not following a policy of duplicating the information. Well, he's basically, what he's telling you is he's assuming that you already know this, because he's writing for a scientific audience, which was a huge mistake. Okay, because the scientists are the last people in the room who are going to get this. The only people who are going to get this are people who are already skeptical of science in the first place, and that have an open mind to new ideas. Maybe a scientist in 100 years will figure this out. Okay, any attention in this present work where we are following a policy of not duplicating information that is available elsewhere, except to the extent that reference to such information is required in order to avoid gaps in theoretical development. The thermal characteristics of individual substances, on the other hand, have not been thoroughly investigated. since they are of considerable importance both from the standpoint of practical application and because of the light that they can shed on fundamental physical relationships. It is appropriate to include some discussion of the status of these items in the universe of motion. One of the most distinctive thermal properties of matter is the specific heat, the heat increment required to produce a specific increase in temperature. Okay, so that's the specific heat. He uses a lot of specific things, specific rotation, but here's the specific heat. The heat increment. How much extra heat do you have to put in to produce an increase, a specific increase in temperature? This can be obtained by differentiating, which makes sense because Larson's is a universe of motion. So he's always going to be giving you the rates of things, and we're going to need to be using calculus to differentiate. And like he did in the chapter before on compressibility, compressibility is the rate of compression. So this is somewhat analogous to the rate of temperature, adding temperature. This can be obtained by differentiating that earlier equation, and so dH over dt equals 2t over n to the third, because the original equation was t squared over n to the third, and so that's what we have, 2t over n to the third. And the n represents the magnetic rotations, or just the rotations. Where does he say? N is thermal motion of magnetic rotational displacement n is only 1 over n to the third of the total. That doesn't quite make sense to me because the atom is 2 magnetic rotational displacements and 1 electric rotational displacements, and he's equating them here. But anyway, okay, 2t equals over n3. Inasmuch as heat is merely one form of energy, it has the same natural unit as energy in general, which is 1.4918 times 10 to the minus 3 ergs. However, it is more commonly measured in terms of a special heat energy unit, and for the present purposes, the natural unit of heat will be expressed as 3.5636 times 10 to the minus 11 gram calories, the equivalent of the general energy unit. Now, I don't know why he's doing this either, because energy is time over space in Larson's system, the inverse of speed. Speed is space over time. Energy is time over space. I don't see why you wouldn't just take a unit of time and divide it by a unit of space to get the natural unit of energy. Anyhow, strictly speaking, the quantity to which that equation 2t over n to the third applies is the specific heat at 0 pressure. But the pressures of ordinary experience are very low on a scale where unit pressure is over 15 million atmospheres. And the question as to whether the equation holds good at all pressures, an issue that has not yet been investigated theoretically, is of no immediate concern. We can take the equation as being applicable under any condition of constant pressure that will be encountered in practice. So he's just saying that at very low pressures, the pressure is basically negligible because the natural unit of pressure is over 15 million atmospheres. And so I'm guessing that the natural unit of pressure then would be a unit of time over the fourth power of the unit of space, because pressure is time over space to the fourth power. We'll see. Or I will calculate that at a later time. The natural unit of specific heat is 1 natural unit of heat per natural unit of temperature. Of course, we haven't calculated the natural unit of temperature yet. The magnitude of this unit can be computed in terms of previous established quantities, but the result cannot be expressed in terms of conventional units because the conventional temperature scales are based on the properties of water, the Celsius scale. The scales in common use for scientific purposes are Celsius or centigrade, which takes the ice point as 0, and the Kelvin scale, which employs the same units but measures from absolute 0. All temperatures stated in this work are absolute temperatures, and they will therefore be stated in terms of the Kelvin scale. For uniformity, the Kelvin notation K, or simply degrees K, or simply K, will also be applied to temperature differences instead of the customary Celsius notation. Okay, this next paragraph is quite long, so we're going to stop right there and start up again tomorrow. I'm sorry to get frustrated at Mr. Larson for all this. I know that, when you're writing something and you're the first person to write it, it's very, very difficult. And he had a task in front of him that was almost impossible. He had very, very little help, very few resources, and received very little support. And so I can't complain about, in fact, I'm thoroughly grateful about what he did. But as a person that's trying to grasp this, I get frustrated because I've read this chapter many times, and I'm still, and the chapter before this, and I'm still having trouble kind of grasping what he's getting at. Although I do think that I'm progressing, and so I hope I can help you guys figure this out a little bit as well. But maybe you guys are figuring it out better than I am, and if you are, please guide me along. Okay, guess that means it's time to stop. And thanks for tuning in today, and we'll be back tomorrow to start again with this chapter on heat. So thanks for tuning in.